Hello students, welcome back. Now let's go to section 3 of this notebook. Alternative means and type 2 errors. What is type 2 error? Let's go back to section 1 of this notebook, which reviews lesson 11. Here's the mathematical structure of hypothesis testing. H0 and HA, null and alternative hypotheses. One and only one of them has to be right. Now, because of those, we can classify errors like this, type 1 error or type 2 error. As I said before, either H0 or HA must be right, and only one of them has to be right. Now, what if H0 is right? And then if I called H0, then no error, no problem there. But if I rejected it, then that's an error, and that's called type 1 error. Error from rejecting the null hypothesis, even though it is right. Now, null is right. That case we covered. Now, let's think about the other case. What if alternative is right? Or, equivalently speaking, H0 is wrong. If I called alternative correctly, then no error. If I didn't, if I rejected it, then that's error, and that error is called type 2 error. So error from rejecting HA, even though it is right. So if H0 is right, then possibility is type 1 error or correct. If HA is right, then either type 2 error or correct. Those are type 1 and type 2 errors. Now the upper bound of the probability of type 1 error is the significance level alpha. And that's something we wanted to minimize. Something like bound by 1%, 5%, things like that. 5% is as big as anything I have ever seen. I've never seen any hypothesis testing with alpha value bigger than 5%. Basically what we want is type 1 error is dangerous, so we want to minimize the type 1 error. In criminal justice system, for example, H0 is assumed innocence. So type 1 error is convicting an innocent person and delivering a guilty verdict. That's bad. I mean, releasing a criminal is bad too, but it's not as bad as locking up an innocent person, or even worse, executing. That's type 1 error. Type 2 error, on the other hand, is something we did not control at all. So significant level and all those z-curve analysis or chi-square analysis we did, they're all about alpha value, limiting type 1 error. Type 2 error, on the other hand, cannot be determined unless many years later, a lot more data came out and we know the precise mu value. If we do, then of course, you can go back and recheck everything and whether the hypothesis testing that took place 5 years ago was correct or not. We can do all those kind of things. Then you can calculate type 1 error, type 2 error precisely. But in present time, you can't really do that. But in some rare cases, you can do a bit of an estimation of beta as well. And that's something we are going to study now. Here we go. The structure of null and alternative hypotheses. And then let's consider another hypothesis. Mu is about the same as mu prime, which we call an alternative mean. That's a term, alternative mean, but this H prime is not referred as an alternative hypothesis. Alternative hypothesis either this, mu is greater than mu 0, or that, less than mu 0. In some cases, just different from mu 0. Those are called an alternative hypothesis. This one is just different. In any case, under this new hypothesis, sometimes we can calculate the probability of type 2 error, or the upper bound of it, the beta value. How do we do that? Well, we'll have to do these kind of computations, but that can wait. Let me try to explain these visually first. Here we go. So this is case 1. Mu is greater than mu 0. Mu is greater than mu 0. So here in the first picture, we have shading to the right with alpha value at 0.05. So that's a significance level. And based upon that significance level and sample size and everything, we can get the standard error and we can get this critical value. So mu 0 is null, critical value. And if my x bar, the observed sample mean, is less than the critical value, so close enough to null, then we accept a null hypothesis. And if it goes beyond the critical value and goes to this red area, then too far away from the null, then we are going to accept the alternative hypothesis. So that picture is something we studied before. Now, let us superpose a new hypothesis, H prime. Mu is about the same as mu prime, and let's suppose mu prime is here. So under this new hypothesis, you get this new normal curve centered at mu prime, and align this x value. This is a critical value. Okay, so this is what we expected, but it turned out like this. So under the new hypothesis, so critical value, so greater than a critical value, then we accept it. Alternative hypothesis, less than critical value, we accept it. Null hypothesis. So mu prime is certainly greater than mu 0, as you can see. So we should have called alternative. So alternative is right. But if I made an error, that means x bar must have fell here in this region. Here or there. So that probability is measured by this area. That's beta. So let's see. Let's look at the first picture. First picture is something we have been studying. So here you go. If x bar no. If x bar had been less than this critical value of x2, then that's it, isn't it? Selecting H0, as a matter of fact, this should be necessary and sufficient, equivalent. Selecting, let me say accepting. So accepting H0, look at the first picture, means x bar falling less than x2. So close enough to null, so we're going to null hypothesis H0. Greater than x2, then too far away from the null, and we reject H0 and going for HA. All right. And then, of course, theoretically speaking, you can get x bar here all the way over here as well. So it's this entire blue thing. That was the previous case under the null hypothesis. Mu is about the same as mu 0. Now, what if we consider mu is about the same as mu prime? Under the new hypothesis, you have to have the second normal curve. And this one, this condition, x bar less than x2, is visualized like this. this a bit lighter blue or greenish shading here. That's associated to accepting H0. You see X bar less than X2. This is X2, same X2 aligned, less than this point. So that's beta. So how do you measure this beta? Well, look at this curve. This is normal curve, and you do the same thing. End minus center over SE. So end is X2 minus center mu prime over SE, and you can figure it out. Now, what if I go to the left? Gonna be like this. This is a standard around the null, and this is a critical point. So if we get X bar less than X1, too far away from the null, so let's go with alternative. Greater than X1, critical point, then close to null, so we go with null. So we can conclude like this. Okay, all right. X bar is greater than X1, then we are accepting H0. But now things are changed. Under the new assumption, under the new hypothesis, mu is about the same as mu prime, then we have the second normal curve. And here, under this circumstance, X bar falling greater than X1 is this part, this shaded part, shaded a little bit lighter blue or greenish part here. That probability is my beta. This red is alpha. This green is beta. By the way, this program is randomized, so if you run it again, you're going to get various different mu prime values. So you see, if mu prime is less than mu 0, all right, but not too much. In that case, there's huge probability for type 2 mistake, type 2 error, greenish part, because mu prime is less than mu 0, yes, but not too far away. So under the null hypothesis, you won't be able to make much of a difference there. So it's more likely that null would win, and consequently type 2 error. Even closer. Now, kind of like this, mu prime is much less than mu 0. In that case, it's more likely that I do it right. So less probability for type 2 error. And then, of course, we're going to talk about these kind of computation, oh boy, in a separate video. A little bit difficult to understand, but we have to do those anyway, so we'll do those, but in a separate video. For now, let's go about those visualization with example problems. Okay, here we go. A group of engineers of a tire manufacturer are testing a new production line that is expected to improve the tire's tread life. Based on the extensive testing, the engineers knew that the tread life of a certain type of tire was normally distributed with a mean of 30,000 hours and standard deviation of 1,500 hours. And a simple random sample of 16 tires made from the new production line yielded the simple mean of 30,950 hours. Okay, got a bit of improvement, but was it a sufficient evidence to declare that we have an improvement? Well, set up hypotheses and test them with the significance level of 0.01, which is something we had been doing before. So it's kind of like this. Normal picture around null, 30,000, and then we get the critical value obtained by n minus center over SE is z-score associated to this 1% here and 99% there, which is about 2.33. I use a little bit more accurate figure. If you look up z-table, you're going to get 2.33, by the way. So if I calculate this critical value, I get 30,870 something here, and 30,950 is greater. Okay, alternative hypothesis wins according to this, all right? Now find the probability of making type 2 error with a sample of 16 tires when the true mean is not 30,000 but 31,000. So we have additional hypothesis H prime, a new hypothesis H prime. So based upon the new hypothesis, we get these kind of situations. This is old case, 30,000, and then this is critical value of 30,870 something. But actually, we improved to 31,000. So 30,800 something or less would have been considered as H0, but we now know that's the error. So we want to find out this beta value. So from the second picture, we can find out the error bound for this type 2 error, beta value. How do I do that? N minus center over SE. So yeah, let me copy and paste that, or maybe I can copy and paste this picture. N minus center over SC. N minus center over SC. Calculate, you get negative 0.34 something. All right, so look up the z-table for less than negative 0.34 something. If you do that, where's my z-table? Negative 0.34 yeah, 0.3669. That's the probability we get. Well, okay, I'll be more accurate figure, 0.366808. That's this probability highlighted in green. That's beta. So how do we answer these kind of problems? Well, in the new picture, centered at mu prime, but aligned with previous pictures so that we have the same critical value that we got before, 3,800 something, 30,872.4, whatever that is. And left or right, which is null? Null is left and alternative is right because the original picture was like that. And then looking for this area using the z-curve. The method is the same, n minus center over SC, find out the z-score, look up the table, and that probability is a beta value here. Make sense? We'd better continue in the next video.